Check. Oh, is this on? No, it's not on. There you go. Hello. Oh, okay. Oop. Good evening. Thank you for coming to the John J. McCarthy Observatory. My name is Peter Miserandino. I am a science teacher at New Milford High School, specifically physics. So tonight we're going to look at some physics and how it connects to astrophysics and astronomy. But before we start, let's see. All right. Clicker's not working. Clicker's not working. There we go. Okay. That should work. Okay. Just a little bit about myself. So I grew up in the Bronx, New York, and I went to Lehman College in the Bronx. And I am a Connecticut certified general science teacher, so I can teach integrated science here at the high school, and I can also teach physics. I completed my Master's of Arts in Teaching at Sacred Heart University. It has a really good master's program for teaching. I've been a teacher here now at New Milford High School for 8 years. Originally, I started as an intern in 2015. And my cooperating teacher, Miss Danielle Raganay, is in the audience over here, right? So she helped me become a teacher, and ever grateful for her support. And then I did a long-term substitute year at Brookfield High School. Then I came back to New Milford High School in 2017. So my first class of graduates is the class of 2018. And I teach honors physics, CP physics, AP physics 2, and also integrated science. That's the 9th grade science here at the school. The first half of the school year, we focus on astrophysics, like astronomy, on a very general level. So what is physics? Well, it's the study of everything. So students will learn about the way that the world works and develop problem-solving skills and be able to perform calculations. So a lot of the students that I teach basic algebra for the CP level, and then for honors physics, it's algebra 2, trigonometry, and AP physics 2. We do electromagnetism, some quantum mechanics in there. So it's a really fun course here at the high school. So what are the topics covered? Oh my God, right? So many of them, and quantum mechanics, right? So we do unit conversions, and we do one-directional motion, falling objects, which fall under projectile motion, Newton's laws, as well as work, power, and energy, momentum and collisions. That's kind of the first half of the school year, sort of the physical sciences, and then the second half of the school year, we focus on electromagnetism. So we'll do some circuits, light, and then we bridge electricity and magnetism, and then we go into electromagnetic radiation. So quantum mechanics is only on the AP2 level, and one of my former students is studying quantum mechanics at UConn. So it's always great when I hear back from students and how they're doing over at their college endeavors. So I'd like to talk about a little bit about projectile motion first. So a projectile, right, is any object that moves through space and is affected by gravity. And there's many types of projectiles. Most people don't realize that just any falling object is really a projectile. So we can throw them at angles, we can throw things straight up. And what better way to demonstrate physics than the sports here at New Milford High School. So any sport that has an upwardly launched projectile this is one of the things that we go through in CP and honors physics, is that if you want to get your ball or whatever you're throwing the furthest distance, you want to throw it at a 45-degree angle so that it'll be in the air just enough time and it'll get the maximum range. So, and then complementary angles at 90 degrees will land in the same spot. So as you can see, like if you kick the ball at 75 degrees or 15, it'll land in the same spot. But the one that's 15 degrees is going to be like a really short time in the air, as opposed to one that's 75 degrees and going high up in the air. And then here's a video of projectiles in motion. So this is a former student of mine, and on Saturdays I run the track. And I said to him as he was practicing, I was like, I'm going to videotape you throwing the disc, and then I'm going to go and calculate how far you actually threw it. But don't tell me. I'm going to come back next Saturday, and then you're going to tell me how far you threw it and see how close I was. So let's give this a go here.
We'll see how
right? So here's the math behind it. I know all of you love math, right? So according to the calculations, the only things that I measured was the time that the projectile was in the air, and I estimated the launch angle. So like I estimated it as a 40-degree angle, and through all the calculations, first I calculated how its horizontal velocity and vertical velocity, and then after that I calculated how high it actually went into the air. So when I came back to Jacob the next Saturday and I said, how far did you throw it? And he said 40 yards. So my calculation was 36.53 meters, which is very close to 40 yards. So, and you know, I would say that he was surprised, but he wasn't surprised because he was a former student of mine. So he knew that these calculations were going to be pretty accurate. So he actually, so that velocity of 19.07 meters per second was its velocity vector. So there's a horizontal component, there's a vertical component, and he threw it rather fast, you know. So a little bit about fast-moving projectiles, right? So, do I have any flat earthers in the audience here? So this might blow your minds, but let's see, right? So a satellite is a special type of projectile. So essentially, it's always falling towards the ground, but it keeps missing the curvature of the Earth, so it goes in orbit, right? So this is how NASA and other entities launch these satellites, and they stay up there somehow. So moving on to Newton's laws, right? So maybe you know these, right? Newton's laws, or you've learned them in middle school, right? So you've certainly heard the first law, that an object at rest remains at rest, and an object in motion. Now, we always add with a constant velocity and in a straight line, because if something's accelerating, it's not a constant velocity, so it's a different inertial frame, and it remains in motion in a straight line unless acted upon by an unbalanced outside force. So this is Newton's first law. And then Newton's second law, if we're looking at pulling this wagon, and I'm using the same force to pull the wagon, well, if there's a small mass, there's going to be a great acceleration, and if there's a large mass, there's going to be a small acceleration. So the sum of the forces is just simply the mass that you're trying to move, or and also the times the acceleration in which you're moving it. Now, acceleration would be the change in velocity. So if it was at rest and then it's in motion, then it's accelerating. And then Newton's third law, so you've heard this one before, and for every force, there's an equal and opposite reaction force. So for students to really understand Newton's third law, so if a boy is pulling on the wall, right, the wall's not going to move, usually, unless he's pulling really hard. But if you change the wall into an elephant, and what's really going on here is that there's force pairs. So if the boy is pulling on the wall, then the wall is pulling on the boy. See how that's kind of like a little bit abstract? But if you turn it into an elephant, boy pulls elephant, elephant pulls boy, and then it seems a lot more tangible when you're talking about Newton's third law. So when you put all these three laws together, let's see a demonstration here.
Ready? No, I'm not ready. I'm not ready.
So what really just happened there? So maybe you've seen the tablecloth trick, right? So if an object's at rest, what does it want to do? Stay at rest. And an object in motion wants to stay in motion, unless acted upon by an outside force. So when I'm pulling on the tablecloth, that's in motion, the books are at rest. If I can do it fast enough, then the books will just remain at rest, as well as all the water inside. And this is always one of the fun demos that we do in physics class. The kids look forward to this one. And magicians are just really good physicists. So whenever you go to a magic show, just know that they're just really attuned to the laws of physics. And then moving on to momentum, right? So with momentum, this is field hockey here at the New Milford High School. So any moving object has momentum. So if a person moves, a ball moves, it has momentum. And then momentum is just the product of the mass times the velocity, very simple. If I have some mass that's, say, 60 kilograms and it's moving at 3 meters per second, 60 times 3, 180 kilograms meters per second, which is funny because there's no actual like derived unit for momentum. And we just represent it by P equals mv. And then another term that you might be familiar with, but it's used less often, is impulse. So impulse we label as J, is just the force times the time. So the unit is a Newton second, but it's exactly the same as a kilogram meter per second. So this is what we call the momentum impulse theorem. So the different name lets us differentiate which one we're talking about. So if you want to talk about impulse, so if a kicker is kicking a soccer ball, if the kicker wants the ball to go the furthest, he's going to have his foot in contact with the ball for a small amount of time, and then there'll be a greater force if he's going to be using the same impulse or momentum. And then we denote this as force is just the change in time, and it's also equal to mass times the change in velocity, and it's just the change in momentum. And usually here at the high school, the way that we teach this to the students, because most of the students that are taking physics are seniors, so this is how we tell them to slow down on the road, because this change in momentum is, if it happens quickly, then there will be more injuries as opposed to moving slower on the road and having time to slow down for things. And here's just a little sample of what we do here at the high school. So momentum, impulse, and action. Maybe you had some children who've already done this here at the high school. We do the Pringles project. So students have to mail the physics teacher a single Pringle potato chip to us at the high school, and it has to land, it has to arrive perfectly intact. And the students love this assignment, this project, because they get to design the box. They have to use non-commercial packing materials for to lessen the impulse, so that the chip will arrive perfectly intact. So just a little sample of some of the stuff that we do here at the high school with the physics, the physical, as like Newton's laws, projectile motion. And now, how does this link to astronomy and astrophysics? Well, it kind of starts with Newton. So when Newton, he took a prism and he took like sunlight and he separated it into its colors, and he called it Roy G. Biv, right? So red, orange, yellow, green, blue, indigo, and violet. So he kind of started it, and all he really just needed to do was take a prism and put it near a telescope, and then you would get a spectroscope. So Newton was really close to inventing the spectroscope, but it was actually Joseph Fraunhofer. And this is the tool of the astronomer. So what can we find out about celestial objects and things that are in the night sky? We can tell an awful lot about what they're made of just by their colors. So this is on the right this is the spectroscopy of the sun. So this is all the elements that are located in the sun. Now you would just think that it's hydrogen and helium, but it's also a lot of other elements, trace elements. And we can see this through its spectroscopy. And when we're looking at planets and we're looking at stars that emit a light, these bands kind of shift. And they shift a little bit, but every single color has its own wavelength. And knowing exactly the wavelength, well, a wavelength is just what it is. It's a length. And if we know how much it's moving and the time it takes to move that distance, then we can calculate a velocity from that. So spectral line analysis, this is one of the things that we're about to teach in integrated science. So astronomers can study the spectral lines from stellar light and determine what they're made of. And the absorption spectra are used to study reflecting objects such as planets and nebula, as well as radiating objects such as stars and galaxies. And then astronomers can use this Doppler effect to calculate how fast an object is moving and in what direction. So the top spectra is an unshifted spectra, and if it's redshifted, the lines are shifted slightly to the right. And then if it's blue shifted, it's moving to the left. So we call it red and blue because when it's moving to the right, it's red, and when it's moving to the left, it's blue. So we just call it red shift and blue shift. And the information that we can gather from spectroscopy and spectral analysis, well, velocity through the Doppler effect. So analysis, this Doppler shift analysis suggests that the universe is expanding. So everything that we see in the night sky for long periods of time, space itself is stretching, because most objects, somewhere near like 90%, 95% of objects are moving away from us. They're redshifted. We can also tell the temperature of these objects. So the wavelength peak emission, the black body curve, in a continuous spectrum, we can actually tell, oh, how hot is this object? And knowing this information, we can study exoplanets. We can actually see the revolution period, and with this information, the distance from their star, what elements are present in their atmospheres, and what composition they're made of. Are they habitable? So many times that's like the question when scientists in NASA, they discover a new exoplanet. It's like, well, is it Earth-like? Is it not Earth-like? So as you can see, as this planet is moving with its partner star, that the spectra is shifting left, right, blue shift, red shift, blue shift, red shift. And we can tell exactly how fast it's moving. So spectroscopy is the major takeaway from astrophysics. We can gather so much information about like what is in the night sky. And my contact info, right? So if you're ever wondering about what we're offering here at the high school in regards to physics, this is my contact information at the high school. I'm always available after school for any students that need help. Physics on Mondays, and I'm also a co-advisor to the Math Honor Society. And that's about it, right? Thank you.
I also want you to enjoy our telescope. We have 160 span of that's our dancers over there. Each 160 years old. And then we have a brand new telescope up on our dome. And really
I turned off the light.
take advantage of all that. Also, the telescope's out of the sky, and I believe it was 5 record.
It was 20 minutes, okay. No, it's perfect, yeah.